To see what happens when we sample a signal, let's start with an analog signal S of t, and then sampling it means to sample the signal at sample intervals capital T, or sampling frequency f of s. So let's remember that the sampling frequency f of s is related to the sampling intervals by a relation of 1 over t. So the sampling frequency is equal to 1 divided by the sample intervals. Just for an example, in ISDN systems, it's used 8 kilohertz as sampling frequency. For audio in CDs, so we usually use 44.1 kilohertz. Some other audio systems also use 48 kilohertz. And mathematically, sampling can be formulated as multiplying the analog signal with a Dirac impulse at the sampling time instance n times capital T, where n is the number of our sample. For causal system, n starts at 0, and t is the sample intervals. So here we have a Dirac sequence, or a train of Dirac impulses. So they're located at time instance n times capital T. So we have n times capital T, and here's our Dirac sequence. So this sequence or this train of Dirac impulses can be written with this equation here. So this delta t here will indicate the train of Dirac impulses, and is this summation with the Dirac impulse at time t minus n times capital T. So let's remember that the integral over Dirac impulse is equals to 1. We can see like this here. And the integral over the product of a function with a Dirac impulse is the value of the function at the position of the impulse. So this is a very important property. So the integral over a product of a function with the Dirac impulse is the value of the function at the position of the Dirac impulse. So this is the mathematical formulation of sampling at time point n times capital T. We can now use this description to compute the resulting spectrum with the Fourier transform.